Goldwasser. She's the RSA Professor of Electrical Engineering and Computer Science at MIT and Professor of Computer Science and Applied Mathematics at the Weizmann Institute of Science. With her co-authors, she's responsible for some of the most influential and sometimes revolutionary papers in theoretical computer science, including papers laying the mathematical foundations to modern cryptography and introducing interactive proof systems to complexity theory. For her contributions, she received numerous awards, including 2 Gödel Prizes, the Tina Lecture Award, the RSA Award, and the Benjamin Franklin Medal. The title of her talk is Pseudo-Deterministic Algorithms.
Can you turn off the lights? Great. Okay, so randomized algorithms, which is something that I haven't seen at least since I arrived yesterday, are everywhere in our field of theoretical computer science. They're being used in cryptography, in distributed algorithms, in sublinear algorithms, in parallel algorithms, routing, load balancing, optimization, approximation, data structures, biological systems. And one of the traditional questions that we always ask in computer science is when we have a randomized algorithm is why don't we replace it by a deterministic one, or can we replace it by a deterministic one? And in some sense, the one way to think of my talk is this really, maybe this is not the right question. So I'm going to restrict the beginning of my talk at least to talk about a subfield that I work in, which is cryptography, and the role that randomness has played in the field of cryptography. So in cryptography, again, if you think about the fact that we're trying to hide something from someone else, even though our algorithms are public, there's something called a key, which is one piece of information that the people who are trying to hide something from someone else know and someone else doesn't know. So cryptographic key is a random key. So obviously randomness is essential and necessary so as to distinguish between me, who are trying to hide something from you. Because if I choose my key at random, you will not know it. And otherwise we really have no other way to say that you and I are different. So cryptography is a field where sort of fundamentally randomness is necessary. And that's true for establishing these keys. It's true actually when you want to achieve a certain strong kind of secrecy, so what we call randomized encryption. It's true for signatures, for something called zero-knowledge proofs, for multi-party computation, for delegating computation. For each one of these applications of cryptography that today are so become kind of a part of our lingo, we need randomness and we assume that it exists. However, in this talk, what I'm actually going to pay more attention to is the fact that randomness is not only used because when it's necessary to use it, but sometimes we use randomized algorithms because we absolutely don't know how to do it, how to solve problems without using randomization. So within cryptography, if we just restrict ourselves to the domain of cryptography, we use randomness everywhere, even when it's not necessarily a must. For example, a fundamental object that we use in cryptographic systems are primes. So people have been talking about the factoring problem. You're factoring something which is a product of primes. Where are these primes coming from? You have to generate them, and we generate them essentially using randomness. And another thing we do is we want to find generators, let's say for cyclic groups. And how do we find these generators? Again, the way we know how to do it is pick one at random till we find one. Another example is finding these squares mod p, a quadratic, non-squares mod p, quadratic non-residues mod p, finding irreducible polynomials over ZP, computing square roots mod p, computing Q roots mod p, finding points on elliptic curves. All of these, I could go for a long list. Some you are familiar with what these mean, some are not. But just take my word for it that these are basic steps in existing cryptographic constructions. Okay, so every cryptographic construction that I'm familiar with does one or other of these steps. And in order to actually fulfill these steps, we don't know efficient deterministic algorithms, but we only know efficient probabilistic algorithms. So some of these things we can do deterministically and based on some assumptions and maybe something is true or not true about Riemann hypothesis and zeta functions and so forth. We have deterministic efficient algorithms. But if we don't want to make any assumptions, essentially to solve all of these problems, we need to use randomization. in order to achieve these tasks. And so that means a lot of us are thinking, how can we replace these randomized algorithms by deterministic ones? Do we absolutely need to use randomness in this case? And again, my question, if you want to think about it, part of what I'm asking in this talk is, should we really care? Do we really want, does it really matter? Why not be happy with these randomized algorithms? Why do we have to go and look for deterministic algorithms? Okay, so now motivation. I just want to say that throughout this talk, from here on, I'm going to speak about what we call search problems, which I think Avi also referred to explicitly. And I know it's a general talk, but still, there's going to be search problems, and I'll have this notation, which is search sub v, and that means that the search problem takes an input, x, and is looking for y. Okay, and what does y mean? The only thing meaning of y is that this v, this verdict function applied to x and y, says yes. So it's looking for a y for which the verdict is yes. Okay, and if y exists, the search problem should, an algorithm to solve the search problem should find y, and if it doesn't, it should say, I can't find it, it doesn't exist. Okay? Often we talk about decision problems as well, but that's not going to be my focus. So a decision problem is just to say whether y exists or not. In the decision problem on input x, you want to find out if there exists a y that will make v of x, y yes. But I actually want to find y, so I'm searching for y. Okay, so our interest is in search problems. And as I said, we're interested in randomized algorithms and asking, are they good enough or should we look for deterministic? So what are the types of randomized algorithms that people usually talk in theoretical computer science? They talk about these algorithms called Monte Carlo and Las Vegas algorithms. How can you tell which one is Monte Carlo? Okay, so this is like the British accent, although it's not British. But in any case, that is definitely Las Vegas. Okay. To put this new work in context, in comparison with these algorithms, let's review what they guarantee for us, these Las Vegas and Monte Carlo algorithms. So the Monte Carlo algorithm, here this table just summarizes what it gives us. If I compare it to deterministic algorithms, okay, the usual comparison is in terms of how much time it runs and what guarantees it tells you about the output, right? And for the Monte Carlo algorithm, just like the deterministic one, these are going to be algorithms we care about polynomial time, so they're going to run quickly. They both run in polynomial time. However, the deterministic one is always going to be correct. So on input x, if the y exists, he's going to find it. Okay? Whereas the Monte Carlo guy, depending on the randomness that the algorithm used, so it's a randomized algorithm, it has a coin, it tosses coins as part of its basic steps. Okay? And depending on how the outcome of the coins came out, it may find y, but it also may make a mistake. So sometimes y exists, it doesn't find it, and it says it doesn't exist. So it can make a mistake, even though with a controllable small probability. So if you look at this summary, it seems like, especially from the mathematicians among us, or anybody really, that it's a clear advantage of a deterministic algorithm. The deterministic algorithm finds y, you know, the probabilistic guy makes a mistake, obviously we prefer deterministic. And then we go to the next variety, you know, the Las Vegas probabilistic algorithm, and that gives us a little bit of a different guarantee. Here the running time, deterministic is always going to be polynomial time. Las Vegas, there's some small chance it's going to run longer, but I'm going to tell you that I don't really care because it's never going to happen. However, what the good part is that in terms of output, both the deterministic guy algorithm doesn't toss coins, finds y and is always correct, but that's also true about the Las Vegas algorithm. Even though it's tossing coins as it's computing, at the end it will give you, it will find y and it will be a correct y. So it's guaranteed. So once we look at it this way, we think, well, deterministic is still a bit better because it's always running quickly, whereas the Las Vegas has some expectation to run for a long time. But what if the Las Vegas algorithm is much faster? You know, most of the time, almost always, except for a potentially small number of coins, it runs much faster. Perhaps you should prefer it. It's not so clear anymore, right, that you should prefer the deterministic one over the Las Vegas one. Maybe a case in point is primality testing, which is a sort of a very telling problem. And in fact, it will make its way into the talk several places. So if you sort of compare Las Vegas primality test and the deterministic, highly celebrated, beautiful work of Agarwal, Kyle, Saxena, which get a deterministic algorithm for primality. So by the way, I said I'm talking about search problems. So primality testing doesn't sound like a search problem. It sounds like you want to know whether a number is prime or not. So what am I searching for? I'm searching for the proof. So I've given a number, and I want to find the proof, something that I can check, that this number is prime. It has to be a short proof. We're always talking about polynomial size. So I can't just list all numbers smaller than and see that they don't divide the prime. So I'm looking for the proof, and I can think about a deterministic polynomial time algorithm as essentially finding a proof for me, right? Because I look at the execution trace of the algorithm, that's a proof. However, the deterministic algorithm for primality, you know, it started order n to 12. I think now it's improved to order n to 6, but I must admit in my embarrassment that this is from Wikipedia. But I venture a guess that's probably true for most of you for the last thing. Sometimes you check that in Wikipedia. But in any case, the proof here is the trace of the execution, which is, let's say, order n to the 6. But if you look at Las Vegas algorithms, okay, that are, let's say, the elliptic curve test with Killian, then, in fact, the running time to find the proof will take order n to the 6, but once you found it, it's very short to check it. Okay, so you can run it once, and then you have time to verify it, and that would be actually much shorter than the time that it took to find it. So there are even these secondary effects of an algorithm, which is Las Vegas, which might produce a much shorter proof, even though it took it coins to find them. So the only point of this slide really is that that when we look at already Las Vegas versus deterministic, even though deterministic tosses coins, and which means that doesn't toss the coins, which means that the Las Vegas guy could take a little longer sometimes, there might be reasons they would still prefer the probabilistic algorithm. Okay, but now I make I go back and I say, no, actually I went too far. There is actually a big difference between deterministic algorithms and Las Vegas algorithms, which is important. Okay, and what is that? Is that if you look at this table, what happens, and something that I didn't highlight in the previous table, is the deterministic algorithm always, when it finds y, always finds the same y. Okay, it's deterministic. On the same input, gives you the same output. The Las Vegas algorithm, even if it always finds y, and it's a wonderful y, and it runs maybe even faster than the deterministic one, depending on the coin tosses that it used during the execution, it might find a different y each time. Okay? So it doesn't reproduce the same y on different executions of the algorithm. And another way I want to think about it is this is an observable difference. So if you run this algorithm twice, think of a sort of black box, you run it twice on the same input, it may give you different outputs, depending on what randomness was used. Okay? And this difference was observed for the first time in work by Lenstra and Bart Smith. This is in a talk that I saw by Lenstra in Lovas's birthday. And Lenstra made this point, is this unique answer, this property of the deterministic algorithm is really a qualitative advantage, okay, of the deterministic algorithm. The work was in the context of what they were looking for is unique representation of a finite field with p to the n elements to use in calculations. And in fact, they defined something called the standard model of FPN, which is a unique model, but it has some extra properties. Now, it's well known that in order to come up with such a representation, if you had a unique irreducible polynomial, you could, that corresponds to having a unique model for FPN. But do we know how to find irreducible polynomials in deterministic time? Okay, so no, we know how to do this probabilistically. What Lenstra and the Smith show is they show how to actually find, using coins, a unique irreducible polynomial, okay, over, that will give them a representation of the field. And in fact, the only probabilistic step in their entire algorithm, okay, is to find a unique quadratic non-residue mod P, okay, which is something that's very easy to find probabilistically. Sort of it's very easy to find one and to test for it, except that the probabilistic algorithms that existed before always came up with a different one. So there were Las Vegas. You toss coins, you really found the non-square, but each time it was a different one. And they showed how to get a unique one. Okay. But my main point is not so much this quadratic non-residue or this application, but this is a clear application where I am doing arithmetic one way over these finite fields, you're doing arithmetic another way. We would like to compute in the same way. Let's say, and therefore we need a unique representation, a unique way to compute, which means a unique irreducible polynomial over this field. I, however, in this talk, want to ask a more general question. Okay, so we think of that as a special case. I want to ask a more general question. When is this possible? So when can we eliminate this advantage of deterministic algorithms? When can we have a probabilistic algorithm which doesn't give different outputs for different coins? Okay, that's going to be my goal. So actually I'm looking for a new type of probabilistic algorithm, which I'm going to call the title of my talk, which is a pseudo-deterministic algorithm. Okay, so what's going to be a pseudo-deterministic algorithm? So the general spirit is this. This guy is confused, okay? He symbolizes an algorithm which runs, he can be probabilistic, I don't care what he is. He runs in, let's say, in polynomial amount of time, okay? And I want it to be impossible for this algorithm to distinguish between a deterministic algorithm, which on the same input always gives out the same output, because there's only one thing it does, it's deterministic, and a pseudo-deterministic algorithm. That's the way I'm going to define pseudo-deterministic, that it's going to be indistinguishable from a deterministic one with respect to this observer. So namely, in the stomach of this pseudo-deterministic algorithm, he's tossing coins. Let's say the first time is the outcome of the coin is 1, second time is 2, 3, and so forth. He has different sequences that he could have come up with, but I want him to come up with an answer in such a way that this guy can't tell what happened in the guts of the algorithm, just by able to supply inputs and get back outputs. Okay? So pseudo-deterministic is you can't tell it apart from deterministic if all you're restricted to is input-output access to the algorithm. So now I'm going to take a little break from my usual talk on this topic and connect to Turing. I will come back in 5 minutes. So, as you have seen already, I think, in David Arel's talk and probably elsewhere throughout these 3 days, this definition is quite reminiscent of what we call the Turing test for intelligence, where there is this inspector, okay, and he's presented on the other side. In my case, was a deterministic and a pseudo-deterministic algorithm. Here, it was with a machine and a man, and he cannot tell whether he's talking to the machine and a man, and that defines an intelligent machine. So this morning, I must admit that I was looking, while I was listening to the talks, I was also looking at the internet, and I found some quotes from this paper of Turing. And it turns out, where he introduces this Turing test, and it turns out that in order to motivate the test, he actually, before he talks about machines and people and asking them questions, he says, let's think about a man and a woman behind the screen. And an interrogator, and he's very nice because he says the interrogator may be of either sex. And the interrogator is trying to distinguish whether he's talking to a man or a woman, and I'm saving you this because we don't have a screen. He says, let's try to think of how we can pretend, how we can make this difficult for the interrogator. And he gives examples of questions that you could ask. For example, here's a question that he gives. Will X please tell me the length of his or her hair? And then the guy on the other side, he's supposing, don't just say long hair or short hair. You could say something like this. My hair is shingled, and the longest strands are about 9 inches long. And he goes on. And after he finishes the man and woman test, then he says, okay, now let's think about machines and try to distinguish machines from men. So I thought that was an interesting, he's very lively writing style. However, going back to math, so this was a prelude to tests for machine intelligence in the paper of Turing. But going back to sort of mathematics, we have used these kind of definitions. These definitions have been very important in cryptography, in the study of cryptography, and the study of pseudo-randomness. Okay, so I just want to show you some other examples of definition of this kind. So when we define zero knowledge, which some of you know, some of you don't know, but let's say a zero knowledge protocol is some sort of interaction between two parties that you want to know that you want to say formally that at the end they accomplish some task. However, the view, let's say, of the parties, the view of this Alice on one side, let's say that she sees the question and the answers that she got in this interaction, she shouldn't be learning anything from it. And the way we define it is because we say that essentially it's indistinguishable from a conversation you could have simulated on your own. Okay, what does indistinguishable mean? It means that if, again, there's this interrogator who's watching, he wouldn't be able to tell apart a simulated conversation from a real conversation. And if that is the case, we're saying the real conversation is given zero knowledge to the participants, in addition to the fact that they actually were in the conversation, and that satisfies them. All right, so I just wanted to say that this kind of definition, where you cannot tell what happens in a real protocol or in a simulated protocol, is the basis for how to, that we use for defining secure protocols in cryptography. Another example where this kind of definition is used is when we talk about pseudo-randomness. So here we want to try to come up with, let's say, deterministic programs that have a little bit of randomness and they generate a lot of randomness. Okay? And we want to say that the outcome is pseudo-random. The way that we usually define it, we say, again, there is this confused algorithm, and he cannot tell apart random, things that are truly random outcomes of a coin flips, and these pseudo-random sequences, which are these kind of messed up coins a little bit. But they're so well designed that in his bounded abilities, this algorithm here cannot tell them apart. So as he can tell you, you just present him a sequence, and he can't tell whether this comes from this pile or from this pile. So this is another place in pseudo-randomness where this type of definition is extremely useful. And interestingly, while I was browsing this morning, it turns out that this problem of randomized computation was also of interest to Turing. So in the same paper, it says, where he talks about machines that can learn, he is writing this paper and he's defining what it means to be a machine and what it means to learn. So when he talks about what it means to be a machine, that part of the paper, he has this quote. He says, an interesting variant on the idea of a digital computer is a digital computer with a random element. These have instructions involving the throwing of a die or some equivalent electronic process. One such instruction might, for instance, be throw the die and put the resulting number into store 1000. Sometimes such a machine is described as having a free will, though I would not use this phrase myself. So interesting that there's a foresight there to this idea of randomized computation. Okay, I'm finished with my detour. Even though in this slide I'm talking about defining pseudo-randomness, which is sequences which cannot be distinguished from random, today I'm interested in these pseudo-deterministic algorithms, which are algorithms which you cannot, even though they are really truly random, they use randomness, you cannot distinguish them from deterministic algorithms. Okay, so this was a nice sort of general introduction to the topic, but let me give you actually a formulation of what kind of algorithm I'm looking for, which is much more in the spirit of how people have defined Monte Carlo algorithms and Las Vegas algorithms. Okay? Let me define this third algorithm called a Bellagio algorithm. People know where Bellagio is? We'll have a slide for it. So a Bellagio algorithm is again going to be a probabilistic algorithm it's a search algorithm. So it gets, before inputs X and it's looking for Y. And the guarantee that I want to give to this algorithm is, one is I let him run in expected polynomial time. So I don't mind the fact that the coins that he might be unlucky very rarely and run longer. But in terms of correctness, what I want is that if there is a Y to be found, you will find it with high probability. Here I said 2/3, but this can be, you can think of this as 1 minus very small. And the newer requirement is that I want that regardless of what coins he tosses, okay, so on input X, whether he tosses R or he tosses R prime, he will come out with the same output. So I want my Bellagio algorithm to, regardless of the coin tosses, with very high probability, come up with the same Y. Just like a deterministic one would. Except I do leave the possibility that there might be some small chance that he will come up with a different Y. Right? So again, these probabilities 2/3 sometimes are disturbing. So just think about this algorithm, that almost all the time he finds Y and it's the same Y, regardless of what internal coins it used. All right, so these are Bellagio algorithms. A special case of a Bellagio algorithm is one where I require unique outputs. Right? So I'm not requiring unique. So in the case of Lenstra and the Smith algorithm, in fact, they managed to get a unique irreducible polynomial. But I'm relaxing that. I'm saying since all I care is about that you can't distinguish this from deterministic, if the probability that you're ever going to come up with another answer is so small that I'll never encounter it, fine with me. Okay? And that will allow me, in fact, to design more of these algorithms than if I required unique outputs. Okay, so why Bellagio? Well, because Bellagio apparently is this particular casino in Las Vegas. And since we're sort of more of the Las Vegas type, that's where the name comes from. But Sanjeev, when I gave this talk in Fox, he suggested that I should call the Kremlin algorithm. Because this is a quote, I think, from your email. Whenever the Kremlin held elections, when the ballot box opened, 95.5% of the time it went to the dear leader. So maybe. Okay, so, but you understand what I want. Okay. All right, so what are examples of Bellagio algorithms? So some examples that we can come up with are from number theory. So finding for when primes are restricted, unfortunately this is not for general prime, but that's an open problem, we can find generators for ZP star, we can find solutions, quadratic Hughes non-residues, extending the Lenz-Schroeder-Smith algorithm. If you go to an algebraic question, you can find canonical, take a polynomial of n variables, which you want to find a point where it's not zero. Okay, so we want to find the unique assignments to the variables that make this polynomial non-zero. I'll talk about this a little bit later. Then we can also look at things that people have done in the past and essentially notice that with very small tweaks, they are actually give you this kind of algorithm that has unique output with high probability. For example, actually the irreducible polynomial problem, you could have done that doing less work if you allow for the chance of a little error. And also, if you think about the perfect matching algorithm of Rabin and Vazirani, you can also think of it this way. Although, in a sense, why do you care? Because you have deterministic algorithms. But it's an interesting algorithm where you have small error, but where you're not going to find the algorithm, but with high probability you will, and it's going to be the same one. But never mind, this is really more massaging things that exist, so it's not so interesting. It's more interesting to come up with these algorithms when we do not have deterministic solutions, or for some reason deterministic solutions are not satisfying enough. So we're willing to go with randomize, but we want randomize with this unique output feature. So more generally, we can sort of show a necessary and sufficient condition, which says that, let's talk about some problem, some search problem sub V. Then a search problem sub V has a probabilistic polynomial time algorithm with these Bellagio type of outputs, okay? Not strictly unique, but unique with high probability, if and only if you can reduce it, it's deterministic polynomial time reducible to some actually decision problem, which can be decided in probabilistic polynomial time. So another way to say this is that if you could find some deterministic question which you know how to solve probabilistically, okay, and then you can show that your search problem is reducible to this deterministic question, then you can actually, by using it again and again, and with the right number of repetitions, you can construct a solution to the search problem, which with extremely high probability will be unique. Okay, so this connection sort of scales up also. I kind of insisted on polynomial time, we're interested in polynomial time algorithms, but you can think of that if you have a sub-exponential algorithm and it's randomized, gives lots of solutions, you still may be interested in a sub-exponential algorithm that gives you a unique solution, and this connection still is going to be true. Just changing polynomial time to whatever time limit you're willing to allow your search algorithm and your decision algorithm. So I realize I've been talking very quickly. So now let me tell you some applications. Why do I really care about this property of uniqueness? And the applications mostly come from the area of cryptography, but not always. So here's one question. So in cryptography, we often have a system involving many people, and we have a notion of system-wide parameters, that everybody in the world should use the same parameters so that when they communicate, they can actually understand each other. And say, for example, they want to come up with a generator. A generator is something very important in a lot of cryptographic systems. And as I mentioned before, we know how to find one probabilistically, but not deterministically. Then how do they agree which generator to use? So one thing they could do is they could say, you know what, Shafi, you do it. We trust you. But the whole premise of cryptography is we don't trust anybody, not even me. So they don't trust each other. What they could do is they could run one of the probabilistic algorithms of the past, each one separately, but then each one would come up with a different generator. However, if they would run one of these Bellagio algorithms, all of them will come up with the same one, and therefore they don't have to suspect that someone has done something fishy to come up with a generator, which is a system-wide parameter. What's another example of an application? So in cryptography, one of the things that we're talking about these days, not only cryptography, also complexity, because there's nothing cryptographic about this really, except the tools. And here the question is, we have clients, okay, and we have servers. Let's say all our work is done by Amazon, by Google, by whoever. I'm actually curious. I wasn't here for the talk of Eric Schmidt, but did he talk about the issue that Google knows everything? Or that didn't come up?
Did not come up.
Didn't come up. Okay, so that's a little bit problematic. So one of the things that we worry about is the following. So let's say that I'm becoming so weak now, since Google is so powerful, and why do I have to be powerful, that I not only store my data there, but I actually ask them to do my computations for me. For example, I could say, give me a generator of this group, and because I have no time to do this myself. However, I have some dignity left, so when it comes back, I say, well, at least I should check. Right? So I'd like to get some guarantee. I'd like Google to convince me that they gave me the right answer, that they ran the computations correctly. And the current literature, the way that's achieved is that we add to the answer some proof of correctness. And this proof of correctness, however, for the whole thing to make sense, has to be much easier to verify than it would have been to do the computation myself, right? So we want this to be much faster and more and shorter than having to run the entire computation myself. And to the best of our ability, at this time, this is what it involves. This is what we know how to do. So this is an example of a solution. And I think this is the best solution that's known right now, at least published. And that is what we do is that the server that did the computation has to also write down a PCP proof, probabilistically checkable proof of correctness. Those of you who know what it is, that's good. And those of you who don't know, you should. So, but this Sanjeev can probably teaches a class on this. But in any case, so the server writes down a probabilistically checkable proof of correctness. He hashes it down. And then this is in this step. But even prior to that, the client has to sort of think of all kinds of queries to the proof of correctness, encrypts them. And this H here is actually something called an extractable hash function. In short, this is very complicated. It uses the most fundamental kind of things that we've come up with in complexity theory and cryptography in the last, I don't know, 20 years. Probabilistically checkable proofs, homomorphic encryption, this encryption scheme, and so forth. So I suggest that if we had bilateral algorithms, we would have a much easier solution. Why? Here's what we could do. Here's a distributed solution. The server now doesn't just go to Google. He goes to Google and Amazon and somewhere else, okay, and asks each one of them to do the computation for him. Okay? And the computation, again, is give me a generator. Now, what do they do? They each have an algorithm, you know, a randomized algorithm. They run it, and they give him the answer. Even if they're honest, this method isn't going to work because each one is going to come up with a different generator. So again, if somebody has a randomized computation and you don't trust them to run it properly, I'm saying let's give it to 3 people. One of them I trust, or let's say the majority of them I trust. They will all send it back, and I can take the majority answer. With randomized algorithms, that's not necessarily going to be the case because each time they'll give me a different answer. Because that's how the randomized algorithm works. It finds a different Y each time. However, if I had a bilateral algorithm, I would be happy because I will always get the same answer. And this way, I could trust the fact that this answer is correct, or take a majority of the answers. Okay, so that's another usage for this uniqueness of the output. What's one more application? Say you are using a probabilistic algorithm as part of a bigger program, and you want to debug this bigger program. So you want to debug the program. However, every time, you know, debugging for those of you who have done it, I used to do it quite a bit. So an inherent thing of debugging is you run the program again and again on different inputs, okay? But the thing is, if you run the program again and again on different inputs, and as a subroutine, there's a probabilistic algorithm that every time you run it, it gives you a different output. It's very hard to debug, okay? So again, if we had all our probabilistic algorithms would be the kind that give the same answer regardless of what randomness they use, that problem would not come up. Now, interestingly, again, in my searches this morning in the Alan Turing papers, I found this quote. And this is Alan Turing in Manchester was working on a project of building a computer called Mark I. And here's some in the memoirs of someone who's writing about this project. And they say, at the request of Turing, an instruction to generate random number from a noise source was provided, okay, into the computer. Unfortunately, the numbers turned out to be not particularly random, so they didn't have a good pseudo-random number generator. And debugging was difficult because programs were not repeatable. See, exactly what I'm saying. Because every time they ran this random number generator, they got a different answer, and therefore they couldn't debug the programs. Consequently, the instructions fell into disuse. So this, as we know, we now have instructions of this sort, pseudo-random number generators, but we haven't really talked about the debugging question. And what I'm trying to say is that if we had randomized algorithms that had all the power of randomized algorithms but gave you a unique answer, okay, then the debugging question would be addressed. Okay, so enough applications. That, here's one last application, I guess. And that is that this is, thinking this way gives you maybe a possible avenue to address problems that have sort of refused deterministic solutions. So what is the problem that I'm thinking of? So suppose, consider the following problem. Primality makes another show here. Suppose what I'm interested in is not cryptography. I just want to find primes, okay? Somebody gives me a length n, how many bits these primes should have in their binary representation, and I'm supposed to give an output, a prime. So randomized algorithm is easy. You pick a string of length n bits, and then you run at random, and then you run a deterministic primality test on it. So we've used randomization to come up with the string, because we don't know how to come up with that string without first choosing at random. All we know is that there are lots of primes, but we don't know where they sit. So since there are a lot of them, if I pick at random, I will choose one of them quickly. However, the best deterministic algorithms, okay, so algorithms which do not just sample a random string and then test it for primality, the best ones around take this much time. 2 to the square root of n, and even more than that. So how about modifying the question and saying, you know what, I am allowing you to use randomness. Okay, you can toss coins if this guides your search for a prime. But I want the algorithm always to output the same prime. So I want it to be a pseudo-deterministic algorithm. On the same n, it's going to give me the same prime of length n. Is that going to help my question? Maybe it's easier. Maybe this randomness is going to help me in a different way than we've gotten used to using it. In fact, here it would be interesting, even if you didn't get to 2 to the square root of anything better, right? Well, that I guess would be much better, because it's a constant. I guess anything better, I mean, better than there's an n here in the exponent, n to the square root of n, would be quite interesting. Okay, so I think this is for me, it's a fascinating problem. We sort of use randomness always in a very similar way, and this would necessitate a different way to take advantage of it. All right, so I'm done with motivation. What can we do? So I think it's a very interesting notion, and I think it has lots of application, and we can do something. It would be nice if we could do more, but here's what we could do. So there are essentially two methods of how we can come up with these kind of bilateral algorithms. And both of them start really from classical randomized algorithms, like classical Las Vegas or Monte Carlo. The first method is what I would call canonize, and this is what Lenstra and Smith also use in their paper, which is they use classical search algorithm, a Las Vegas algorithm, to find a solution, a y. Every time we would find a different y, and then they show how to convert that y to a canonical y, to a unique one. Okay? And also in some of our applications that we do. The second one is different, and that is it's a way we show that you can reduce search to decision in a fairly standard way. It just hasn't been used for this purpose or in this context. So we reduce search to decision, and then we use classical randomized algorithm to solve the decision problem. So again, we use randomized algorithms that exist, Monte Carlo type, okay, and then reduce them to search in this way to guarantee unique output. So there are two sort of different methods. How many mathematicians are here now? It's not really higher mathematics, but okay, I have 2-3 slides that actually have some math on it, okay? So for example, how would you find a generator, one of these kind of canonical generators, or generators which are unique with high probability for ZP star? So this is work with Eran Gat from Weizmann. So let's look at a case, okay? As a simple case where the prime looks like a multiple of another prime, so k times q, q is also prime, plus 1. So the thing is, this is a very restrictive case because we want k to be of this size, okay, just polynomial in log p, which means that this prime q is quite large relative to p. And in this case, here's a way to find a generator which will be unique. First step, we'll just find a random generator using Las Vegas algorithm, okay? And second step, we'll canonize it. So we will make it into a unique one. The first step is kind of well known, and it's just select a random G, okay, in ZP star, and check if it's a generator. How do you check something is a generator? If you know how to factor p minus 1, which we do here because we started with this p minus 1 equals to k times q for a large prime, it's very easy to check. So we found one, but it could be a different one each time. By definition, it will be a different one each time. Otherwise, we wouldn't have found it. We had to choose a random to have a guarantee that we'll actually hit one. So now you need to canonize it. And again, this is also very simple. All you need to do here is to make the following, the insight here, which is also very similar insight in Lenstra and the Smith's algorithm, is that if you take these two generators that you found, let's say by sampling at random, Okay, you can define the set, which is a small set, it's a small list of elements, starting from G1 on the left, starting from G2 on the right, taking them to the power Q to the I, where I goes 1, 2, 3 up to K. These two sets, even though we computed them in different ways, are the same set. And because they're not in the same order, but we can sort them. Okay, and once we've sorted these two sets, they're the same set, and I'll take the smallest element in it. That will be a canonical element of a certain order, and then I'll find something from another order, take their product, and that will be my generator. But the issue really not so much how to find a generator. The issue is here that the method here essentially shows how to compute some small list, okay, and then takes the smallest. So some sort of lexicographical ordering takes the smallest, and that's how you get a unique element. And in the Lenz-to-the-Smith case, essentially they found 2 square roots of some square, and they took the smallest one. So that was, and their list was of length 2. Here the list is a little longer, but it's, I think this is sort of a way to describe this method more generally. That you're looking for a small enough object that you can enumerate all possibilities and put an ordering on them. What's another example? So the other example was, that I said from algebra, was how about finding a Bellagio algorithm, finding non-zeros of polynomials. So here I have a polynomial, let's say on n variables, and let's say that the sum of the degrees is d. And this is a problem that's very well studied. In theoretical computer science, we're very interested in the answer of whether we know how to solve this problem. Oops, sorry, too many clicks. We can talk about, sorry, it's stuck. No? So we can talk about a decision question and a search question. The decision question is this polynomial identically zero? Is there a place actually, is there assignment to the variable which makes it non-zero? And a search question is find an assignment to the variables which makes it non-zero. Okay? And we don't know how to solve this problem in deterministic polynomial time, but we do know how to solve it in probabilistic, using probabilistic algorithms. Oh my God. Okay, yeah, that's my usual thing. Alan Turing was very lucky that he was a theoretical computer science. Okay. So we have this algorithm called the Schwartz-Zippel algorithm, which is very nice. And the idea there is that you essentially choose at random values for the variables. And if you use them, you choose them at random from a small enough set, which is related to the degree of the polynomial. Then, and then you assign you check whether the polynomial of these random choices is equal to 0 or not. And if it's equal to, if you come up with 0, even though you only tested it's equal to 0 on these R1 through Rn, you say, you know what, I think the polynomial is identically 0. There's no other place where it's non-zero. Of course, if it comes out not 0, you know it's not identically 0. So you can say output the random values which make this polynomial non-zero. Okay, and the Schwartz-Zippel lemma tells me that this is a very good procedure, that if the polynomial was identically 0, we're always going to be right. We're never going to find a point where it's non-zero. And if the polynomial was not identically 0, then with high probability, okay, I will be able to find R1 through Rn, which will make it non-zero. Okay? However, if you think about this as a search algorithm, looking for the values R1 through Rn, every time I run this algorithm, I come up with a different setting of the variables, which makes the polynomial non-zero. And I want an algorithm which will give me the same value for the variables, okay, x1 through xn, which makes it non-zero. So how do I do it? So how can I come up with an algorithm that every time I run it, it's randomized, it will give me a setting for the same setting for the variables, which makes the polynomial non-zero. Okay, so it turns out to be very simple. We do this by reducing this question, the search question, to the question of actually testing whether a polynomial is identically 0 or not, a decision question. Okay, and I know this is a general talk, so anyway, shall I put this slide up? It's a very simple transformation, with the idea being essentially that we reduce the setting of the variables, x1 to a certain value, x2 to another value, x3 to another value, and so forth, to every time we set the value of a single variable and then test whether the remaining question, which is now a variable with a polynomial in n-1 variables, is identically 0 or not. And by doing that, I can essentially find setting for the variables which is unique with extremely high probability. And I can set that probability as I wish. So I think that that's probably enough for this application. In fact, the way that this algorithm works, going from decision to search, is what leads to the general theorem, which is, sorry, God, something's gone crazy here. Okay, one more. You think? I don't think so. It's never happened to me before. Okay, I mean, it has happened, but not in this talk. This reduction between decision and search for the case of polynomial identity testing, finding a point where the polynomial is non-zero, is actually a special case of a general characterization, which is the theorem that I mentioned in the beginning, where you can do this for any search problem. If you can reduce the search problem to some decision problem, it could be any decision problem. In the case of the polynomial, it's a very natural one, whether once you set a value for one of the variables, the remaining polynomial is identically zero or not. But more generally, if you can find any decision problem that you are deterministically reducible to, and which you can test in randomized polynomial time, then you get one of these Bellagio type of algorithms. Good. And furthermore, this characterization immediately yields some more examples of Bellagio algorithms, like finding unique irreducible polynomials in a different way than the Lenstra-de-Smith, and like finding unique perfect matching in the Vazirani and Rabin algorithm. So you can now ask a question. Say, okay, define the class, define a new algorithm. Maybe it's true that if you require a randomized algorithm to always give the same answer with high probability, maybe these are exactly the same kind of problems that can be solved by deterministic polynomial time algorithms. Could be that you've somehow restricted the kind of problems you have to such an extent that you fall back into deterministic algorithms. That's one question you can ask. An alternative question you can ask, maybe being Bellagio is exactly the same as being randomized. So everything that's randomized algorithms could actually be randomized with the unique solution, but it's still different deterministic. Okay, so you can ask these kind of questions, and in fact, we can show certain things. First of all, if in fact there's a difference between randomized algorithms and non-deterministic algorithms with respect to polynomial time, then there's also Bellagio algorithms, which are not in polynomial time. That's an answer to the first question. And the second question is that there exists actually search problems that are solved in probabilistic polynomial time, but don't have Bellagio solutions. So this is a non-trivial class.
Does this happen every time you run the talk?
It only happens in Princeton.
So I mean, it's not a Bellagio talk.
It's definitely not a Bellagio computer. I want to dedicate my last few minutes to say that this notion of pseudo-deterministic algorithms is not just relevant to talking about sequential algorithms. So any setting where you're sort of randomness bound, where randomness is very significant, this is an interesting question. And now, two examples of such settings are distributed computation and sublinear algorithms. So let me just say a word about each one of these areas. So these are areas where randomization is extremely useful. In order, sometimes there are some tasks in distributed computation where we can prove that there are no deterministic solutions, okay, and that there are some tasks, essentially, the sublinear algorithms do that is, again, you can sort of prove that you cannot do it deterministically. So an interesting question is, okay, we know you have to use randomness, but can you modify your solutions to give always the same output? So let's think about the distributed setting. A very well-known problem in the distributed setting is that there's a bunch of processors, and people think about, usually they use the term Byzantine generals. They all have inputs, and they want to agree based on communicating with each other, based on their inputs, whether to attack or not to attack. Okay, so they want to know, they actually don't really care if they attack or not, interestingly. They just want to agree. Say, attack, everybody attacks. Don't attack, everybody doesn't attack. As long as we are in agreement. And it's well known, in fact, Mike Patterson is here, that it's impossible to do this. So if one of those generals is faulty, okay, so he doesn't behave according to the rules, then a deterministic algorithm cannot actually solve this problem if there's asynchrony. Asynchrony meaning if they don't, maybe I didn't get a message from a general because he's late, or maybe he's faulty. So if you have asynchrony in the system, you can't distinguish these events, and it turns out it's impossible to agree. And if you restrict yourself even to synchronous solutions, then there's some bounds on how much rounds of communication between generals have to go on till they agree. However, miraculously, it really is miraculous, with randomization, Michael Benor, I think it's like 1982, he showed how you can agree. Just have a very beautiful randomized algorithm, and not only it's impossible, but it's possible. And moreover, a later algorithm by Feldman and Micali shows not only that it's possible, but you can do it in constant number of exchanges. We can agree in asynchronous case and synchronous case. So the ability of toss coins sort of breaks this impossibility. However, interestingly, they agree, they toss coins, and then they agree whether to attack or they don't attack. But depending on the outcome of their coin toss, they might decide to attack or not to attack. So in other words, they all can start with the same inputs. They're all tossing their own coins, okay? Then they come to an agreement. And the agreement is they agree. They will all run in that direction or run in the opposite direction. However, it could have been, that in the next day, if they would have tossed different coins, they would have agreed to do exactly the opposite. So you can ask in this setting, a very natural question is, can you make algorithms which are randomized, so they take advantage of the fact that there's a coin to get over this impossibility, but they always come up with the same output? And the answer is yes. So you can do that. Of course, you need to define what you mean by pseudo-deterministic distributed algorithm, which is a little different. Here there's a bunch of parties, not a single algorithm, but the algorithm is defined really by a bunch of communicating computers. And let's say they're also tossing coins, and there's corrupted computers, and you want to sort of compare the situation. You want them to toss coins, and you want to say that in a deterministic case they don't toss coins. In a probabilistic case they do toss coins, but you still want to have this feature that regardless of the outcome of the coins, they come up with the same answer. And that's how you'll define it. And since there are corruptions, it makes the definition a little bit more complicated. You want to say even in spite of these corruptions, you cannot foil this property of having the same output in both executions. And it can be achieved. Okay, go. Very nice. Okay, let's skip ahead. Sublinear algorithms, right? Sublinear algorithms. That's another setting. So what's a sublinear algorithm? A lot of text here. But the idea of sublinear algorithm is this new quest in computer science to try to deal with the problem of big data. Right? So we keep talking about there's lots of data out there, and we don't even have time to read the data in order to reach a conclusion. So how can we sample the data and still reach conclusions? We have these sublinear algorithms. For certain problems, you can make you can reach outputs. And then we talk about making queries to the input, and we talk about how many queries you make. And little o of n here means you make even less than linear. So you're not reading the whole input. And this is, again, an area where randomization is extremely important. But again, the outputs are going to be different for different randomness. And it's a very interesting question, which we're still studying now, whether you can guarantee some kind of uniqueness of the output. And the verdict is out on this. So in some settings, no. But in some settings called promise problems, maybe yes. So that's all I wanted to say about what we know. And now 2 minutes for open problems and directions. I think this is one of these fields which I think is an interesting concept. And there's a lot of open questions, much more than what's known. So let me just throw some of them out there. And I guess I've mentioned some of them during the talk. So given x, find a unique prime in the interval between x and 2x. Okay. How to find the generator for prime p without the restriction that I had. The p is equal to kq plus 1, but for general primes. Can you show that can you show that you can reduce every Las Vegas algorithm to a Bellagio algorithm? Or can you show that you cannot do it with respect to black box reduction? These are the standard questions we ask, but asking it about this concept. Can you make a PowerPoint presentation in Princeton without it looking this way? That's another open question. Yet to be determined. If you invite me again, we will have another sampling point. I think that that's actually an interesting question, not just in the context of theoretical computer science the way we know it, but if you look at algorithms like there's a lot of algorithms for doing route planning for robots, okay? And they inevitably use randomization. They use sampling in order to sort of figure out a plan. And in that case, if you have two robots and they're using these algorithms, you certainly want to make sure that they don't collide. So it's again another sort of natural setting where you might want this extra requirement that regardless of what randomness you've been using, your decisions are unique. And my last slide is that in some sense, in the setting of algorithm design, I think it's a very useful feature to have always the same output. But if you think about it in the settings of experimental science, it's even more important. So in experimental science, I guess the fundamental requirement is that you can reproduce your results. In some sense, that's what the truth is about. If you can reproduce the experiment, then you found something that you can publish, which I guess is equal to truth. And since randomness seems to be such an integral part of algorithms that will handle large data size, which are currently available in sort of science discipline, I think it's a very interesting question. How do you define pseudo-determinism for algorithms in that context? Thank you.
Questions?
Yes.
Shafi, great talk. I mean, I love the concept. So at a very low level, maybe this is too low, but an algorithm like quicksort, right? Oh, I'm sitting next to the world expert. Bob's here. I should let him ask. But quicksort uses randomness, and you get different answers. And obviously, you can
get the same
sorting
answer.
applications.
You mean you get the same answer?
Well, if the keys...
Different performance.
It's not a stable algorithm. So if you have a record and you have identical keys, they'll get swapped.
Yeah.
Right. So if you then, if you sort and then hash, you'll get different answers. I mean, there are applications in the real world where quicksort's not stable. So if you could build a Bellagio quicksort, but roughly the same performance, that'd be huge.
Right. So just as something that it invokes your question. So my first reaction was, but quicksort at the end is the same output because you sorted, and then in which case a Bellagio is not interesting. But my second reaction is that what you're saying is something much more. You're talking about the execution of the algorithm, and that you're talking about the execution of the algorithm. I was saying that you black box, but in fact, most applications in the real world that are interesting, where this could be interesting, is that the execution is different depending on the randomness that's used. And that may mean something in terms of the performance, right? In multi-core, in terms of debugging and so forth. So you're asking extra, something more than the input-output being the same. You're asking that some intermediate invariant will be the same.
But I'll say a lot of that, but typically in the real world, you're not just sorting the key is attached to a value.
I see what you're saying. Okay, I see what you're saying. Right. Good. Got it. Yes. Okay. Got it. Yeah. Okay.
So
Good.
Stability.
Right.
And in the real world, most people can't use quicksort because it's not.
Because it's not stable. Right.
So you would make
right.
Bellagio quicksort would be stable.
Got it.
I mean, it wouldn't be stable, it would be pseudo-stable.
But is, again, pseudo-stable good enough?
It's very good. No, it's great.
Hello?
Yeah.
I'm confused, and there's probably several ways to ask this question, but the easiest way would be, how can a polynomial time observer even conduct the indistinguishable experiment if the randomized algorithm does not halt in polynomial time?
Does not halt?
If the algorithm it's observing doesn't halt in polynomial time.
Okay, good. So the question is, what's the chance that you're going to see a run like that?
It doesn't matter. You said it was indistinguishable. You didn't say there's a probability of it being indistinguishable.
Okay, so I guess one thing that I didn't emphasize, although I think it was in the slides, is that all our observers, they're very limited in the following sense that they can run in polynomial time. So our observers for the definition of zero knowledge, for pseudo-randomness, for the pseudo-deterministic, they only have polynomial time to run in, which means that I only care about events that they are likely to witness in polynomial time. So if that probability is smaller, okay, let's say if it's especially small probability in polynomial time, that's never going to happen.
While the other algorithm is running, does that count against the observer's time?
Okay, good. So this is a great question. So what you're saying is your definition doesn't take it out. Your definition does not take into account that maybe the randomized algorithm is slower than the deterministic one, or they're at different times, right? Or different executions. You run it twice, it runs for a different amount of time. That's a way to tell them apart, right? So good question. And of course, this was sort of an abstraction for the purpose of the talk. But you could, and I was sort of ignoring that. I was saying, and that's why Bellagio algorithm actually doesn't have that general definition of pseudo-determinist, of just observing the behavior. However, you could, for example, slow down your algorithm to run the same amount of time on every execution regardless of the randomness. So you would put some upper bound on how much time it takes regardless of the randomness, which works, let's say, for most of the randomness, and that's how much time you would run even if you already found your answer. Yeah.
Actually, I have maybe a naive question here. So when you assume randomness and random number generators, do you assume that they're actual random number generators, or because I mean the naive way of thinking about this would be to hardwire seed on a random number generator and get always the same results.
Right.
So I'd like to know what I'm missing.
So that's
here.
a question that always comes up. So people say, look, if all you're worried about getting a unique answer and you have a good randomized algorithm, why don't you just fix a seed and run a pseudo-random number generator? So my answer to that is that if you fix a seed, then then I cannot really claim anything about the behavior of the algorithm. All I can claim is that with respect to that seed, it's okay. And second of all, we need an arbitrary number of, we need long randomness, right? So the only way I know to go from small seed to large seed, we need, again, computational assumptions. So here we're making no assumptions. We just have the same output. Yeah.
So my question's a follow-up to that one.
Yes. Hi.
So I understand why, to get the answer, you need real randomness. But you also mentioned a good thing about the Bellagio algorithms is that they help you debug. So I don't believe that for a minute. Here's why. First of all,
okay.
Right? You're still using randomness. You'll get the same answer, but the actual run for the Bellagio will be different. You'll still have trouble debugging. Two, any random algorithm is easy to debug. Just use what we just said, which is for debugging purposes, fix the string of randoms that you're using, and every time you debug, use the same string of randoms. You won't have the good properties you want for the answer, but you'll have perfectly good properties for debugging.
Okay, so I have an answer to your first question and to your second question. So for your first question, I was assuming that the randomized algorithm was not the buggy part. So the randomized algorithm was error-free, but I was using it inside of a larger application, okay, which had bugs. And I was worried about the fact that this larger application, every time I'm trying to do, it makes a call, and every time it gets a different answer, and now I cannot reproduce for the larger. So that's the answer to the first question. And for the second question, my answer is the same as I answered before. And that is, if you fix the seed for the purposes of debugging, you're not debugging the real program. Because if this program needed a probabilistic algorithm, it must have been important for its performance or correctness or whatever, okay? Once you fix the seed, you're debugging it for the run with this seed, which I don't know that this program that you are debugging actually has the same behavior as the program that you're interested in. So you'll fix the seed, and you will get the reproducibility, but is it really getting the same properties that you... So I don't know that the probabilistic algorithm is working correctly now. Maybe for this seed it doesn't. I'm giving you the guarantee that regardless of the randomness, I will have the right property. Right? The whole thing about randomized algorithms it's important that I tossed coins. If I fix it, it's not randomized anymore. And therefore, if I needed that for my application to work, I'm not getting that anymore. So it's the same answer as for the fixing seed solution in the context of debugging.
Question over here. Would it help any if you relax the requirement to have the exact same answer and you're willing to have the answers all be equivalent up to some epsilon?
Say again?
If you're willing to relax the requirement to get the exact same answer to the requirement that you get almost the same answers up to some epsilon that you're given in advance, could that make devising algorithms easier or maybe change?
That's exactly what I did. So my definition is that I'm not requiring the same answer. I'm requiring the same answer with high probability. So there are some coins for which they would give different answers.
I'm not saying the same answer with high probability. I'm saying that all the answers are going to be within epsilon of one another.
Right. Interesting question. Yeah, I've contemplated the idea, but I don't know what to do with it. That's a very natural. It's a very natural definition, especially in the context of what we call property testing, where you want in some sense even the answer to be correct for an input which is near your input.
Because in many of your applications, that's all you really need.
Right, so you want to maybe relax it even on the output or on the input?
Output.
So I thought in the context of biology, maybe that makes more sense, yeah. To have some distance between them, according to some measure. Yeah, I agree. Good point.
So thanks, Shafi, again.